So, this LDO is quite simple to use. As you can see there are just two resistors that you have to install on your LDO that you buy, and put an output capacitor C out and then an input capacitor, and that is all that is required for this circuit to work. And so, let me give you an overview of this LDO types. Okay. LDO, when you want to buy, you do not have to worry so much about it, but it is important to know what are the types of LDOs which are available to you. You will get NCMOS or NMOS LDOs and PMOS LDOs. Okay. Alright. So, you can, so where are they used and in what conditions do they is each one of them used. Thing is, if you are looking at input V in, V out, okay, typically in the range of, let us say 1.5 volts at the input and regulated 1 volt at the output, okay, then you can be more or less sure that it must be a NMOS kind of LDO, because that is what ultimately, I mean, that is what people most of the companies which give you offerings will actually use as a technology. You can have this 1 amp even at 1 volt even at 1 amp. So, you will be dissipating 1 watt, but the difference, the dropout is only 0.5 volts, right, and if it is 1 watt, if it is 1 amp, you only have 500 milliwatts of dissipation. You do not need any great heat sink, between input and sorry, let me show input this way, IP and IO, right. You are dropping only 0.5 volts, and the current that is being drawn continues to be 1 amp. So, it is about 500 milliwatts. So, that is typical of what an NMOS that you can buy in the market. PMOS on the other hand is perhaps not with this kind of input voltage ranges, but it could be much higher. Okay. You can have, let us say 3 to 36 volts as an input, okay, and the output is also configurable. Let us say you can configure it to 12 volts and so on and so forth. If this is the kind of configuration, you can be more or less sure that this must be a PMOS based LDO. In other words, all that means is the series pass element is either an N MOSFET or a P channel, N channel MOSFET or a P channel MOSFET, that is all it means, it does not mean anything else. In other words, if you go back to this picture, let me redraw the picture. You look at this picture here, this you can see is typical of what you would call a NMOS MOSFET series element, right. So, in an NMOS series element, what would you do? This V in is typically connected to the drain, which is VDD, the output is taken from the source, and the gate actually is the error amplifier output essentially is being driven by this system in order to keep the system in regulation. So, this is typical of what you would do in a N channel NMOS N channel or N MOSFET series pass element. If it is PMOS, you just reverse and then build the circuit accordingly, right. So, but you can see that whatever be the series pass element, the circuit remains the same. The external, for the external viewer, for the designer, it continues to be the same, and the issues that we discuss are also the same. So, really you should not worry about whether it is NMOS or PMOS, but you should keep this in mind, right. Okay. Now, I must also draw your attention to this little thing I mentioned to you about the let me go back and show you something about, I am just trying to see if I really explained that. No, it appears I did not. So, let me quickly explain that part as well. So, that will help you connect several things in this course. Okay. So, let me redraw, and for convenience let me redraw this n channel the series pass element based or N MOSFET based LDO internal circuitry. What will I do? I will draw the okay, let me yeah, that should be fine. The space may not be sufficient. So, what I will do is I will take a fresh sheet and we will draw from here. Okay, very good. So, I go like this, right, and I take the gate. This is NMOS N channel MOSFET. So, if it is an N channel MOSFET, this must be the drain, this is the source, and that is the gate. And what I do? I need to provide the feedback. So, this is R1 and this is R2. This is the point where I sense, and I will be connecting it to the error amplifier, to which is connected a Vref, right. The output actually drives the gate. What is this point? V out. What is this point? V in, and this is Vref, and you can see this is quite simple to do. Obviously, you can't take the V out without providing, without looking for the stability, without adding the stability capacitor, which is very critical, right, and then you have the load. This is RL, this is C out. I also mentioned to you that we need an input capacitor, and that is C in. This C out you have to be very careful, because it is the one that provides stability to this voltage loop. In other words, if you take a capacitor's equivalent electrical circuit, you would put one parasitic resistor in series and one parasitic resistor in parallel, right. This is providing or giving problem. This is a capacitor, this is the series, and this is the parallel resistor. These are two parasitics, you will not see them, but they have their effect on the performance of this capacitor. So, what is this effect of this? The effect of this series resistor is to reduce the efficiency of storage of this capacitor, and this parallel resistors problem contributed by this parallel resistor, leakage, right. Leakage is an issue with this. This is giving you problem with respect to efficiency of storage. Storage efficiency takes a beating, because this resistor drops the voltage across itself and then does not allow you to charge. So, the rate at which a capacitor is charging will have a huge bearing on the series resistor, which is basically a parasite on the capacitor. So, it has everything to do with charging, rate at which it is charging, and the efficiency of charging. Actually more than storage, it is more about the efficiency of charging, and then of course leakage. So, you have to choose, you are trying to regulate a V out here, and if you choose a capacitor which has a high series resistance, obviously this is going to take a problem, this is going to take a beating, right, because this is exactly what you do not want. You do not want this V out, you want it to be precise, accurate. We gave out all those specifications and you have to actually meet those specifications, right. Let us see what else you can do with that, so essentially what we are saying is that this C out resistor is important. So let us move on with this NMOS and CMOS discussion, series pass element discussion. See, this one is being an NMOS series pass element requires at times, depending on how this output voltage increases or decreases, there might be a situation where this gate voltage will have to be greater than the output voltage. It might have to, it actually turns out sometimes like that, which means what would happen? Let us say the input is not, see basically the output voltage, if it has to be if the gate voltage has to be greater than the output voltage and the output voltage is lesser than, has to be always less than, V out has to be always less than V in a LDO, and you need a VG gate voltage greater than sometimes V out. Okay. How do you generate this situation? How do you come out of this situation? Well, typically they use a charge pump or an external V bias, and and then we will have to provide this higher voltage in order to ensure that this NMOS series pass element actually works. Again, you do not have to worry because all of this is actually implemented inside the chip, an LDO chip, and it is of no issue for you and you do not have to really worry about. But nevertheless, you should know that there can be a situation where the gate voltage has to be given higher than that of the source under certain loading conditions. Let us go step by step and understand these loading conditions carefully, and let us see exactly how this LDO actually functions. For that, what I will do is I will draw on the x axis and on the y axis I will draw VDS. Okay, I will draw VDS, and what is VDS? It is nothing but V in minus V out, right. This is VDS, which is V in minus V out, and on the y axis I will show the load current. I will show the load current. So, we will say drain current, nothing but the drain current, right, that is nothing but the drain current, or also nothing but the load current. So, alright. So, what would you show? I will show the saturation line. This is the saturation line essentially, and I will take an example, okay, of, assume that you are interested in V in of 5 volts and V out of 3.3, 5 volts input, V out is 3.3 and load current I out is 500 milliampere max, basically, right. Maximum current that this load can draw will be 500 milliamperes. Of course, it will depend on, this load is always varying, right, it is a dynamically varying load. Sometimes you can have microcontroller, sensor and all peripherals connected to it, and therefore it could be drawing a very high current. Sometimes only the microcontroller may be on with all the other peripherals going down, which means the current could be going down. Okay. So, it is a dynamic situation, and all of that essentially means this RL is never fixed, it is always changing over time, and this regulator has to ensure that this regulator has to ensure that irrespective of what how the load is varying, it has to keep the system under high regulation. Okay, so if you wish to mark that point, let us say this is 0.5, this is 1 volt, this is 1.5 volts, and this is 2 volts. Okay, this is the voltage that you want. So, VDS is nothing but V in minus V out, which is nothing but the drop voltage, right, drop out voltage. That is the voltage that should be dropped across this series element, that is the voltage that has to drop across this series element. Here you can see it is quite simple, V5 if V in is 5, V out is 3.3. So, VDS is nothing but V in minus V out, which is 1.7. So, 1.7 comes somewhere here, let us say, alright. And now let us take drain currents, let us say your 0.5 amps, which is the maximum load current, point comes here. So, let me draw a line like this, 1.7 comes here. I am sure you will all agree to this point. Okay. Now, so here you have a situation where the requirement is that, yeah, so you have 1.7 and this actually corresponds to the drop which is 1.7 and the maximum current which is 500 milliamperes. What you perhaps do not know is which you should actually know at this point is what is the VGS for this point to remain. Let us put VGS as 3 volts, indeed it is 3 volts. If you give a VGS of at the gate to the source, between the gate and the source of 3 volts, this system will give you a drop of 1.7 volts across VDS and will be able to give you a source, I will be able to source a current of 3 volts. Let us call this as some point, let us say X, right, or some point here. Now take a situation where the load current increases and let us say it goes to 0.7 volts, 0.7 amps. So, let me draw it for clarity again, so that you will see the picture better. This is 0.5 and let us say it goes to 0.7, right, and that is here. Okay. Now, you do not want to, so essentially what you have to do, so this is the key here, right, only the load current has increased, you have to continue to maintain the same voltage drop across it, but unless you do something to ensure that you have to do something which essentially when I mean something, unless you increase the VGS to 3.5 volts, you will not get it back into regulation. So, you can see that unless you increase VGS, the load current sourcing the required load current will not be possible. Okay. So, I think what is important here is, for some reason it has, I have written here 500 milliamperes max, but it is possible that for some transient condition it may even have taken. So, I will remove this word max so that we do not violate this discussion point here. Okay. So, this let us say is point y, this is your point y. Okay. So, that is point y. So, here you have to give the additional VGS so that it actually moves. So, look carefully, you have not violated this voltage drop across VDS, but you continue to keep it exactly at the 1.7 that is required. Now take another case, alright. You take a case where input reduces, you take a case where input reduces. If input reduces, graphically you have to keep your basically you have to, if you want to keep this point in saturation, if you want to keep this point in regulation under the condition where V in changes, when there is a reduction in V in, you want to keep this point in regulation unless you essentially reduce this drop, you can't do that, right. That is the key here. Unless you reduce this drop, you will not get back V out that you have planned for, whatever that you wish to that you wanted to, you have designed it for. So in other words, here you can see VGS line has remained the same, only thing that the point has moved back. In other words, you have gone in the direction of reduction in VDS, this drop, you are playing with this drop, and let us call this point as Z. So essentially this LDO is moving from X to Y to Z and so on and so forth, based on either change in V in or change in any conditions at the output due to change in the output load condition. Let us output load conditions. Let us do some simple Ohm's law and demonstrate a simple concept here, which will allow you to understand the whole discussion quite well. Let us just put back these two things. You will see that your drop is 5 volts at the input, V out is 3.3. So if you do if you want to calculate the resistance R, this will simply be 5 volts minus, sorry it is not coming out well, so let me write it here. Let me calculate the resistance R. For some reason I want to calculate R, let us say 5 volts minus 3.3, maximum load current of 0.5 amps gives you 3.4 ohms, right. You can substitute any number of values if you wish. What it means is this series pass has a resistance of 3.4 ohms, nothing else. In other words, supposing hypothetically if you replace this with a fixed 3.4 ohms resistor, you can give V in of 5 volts and you can take an output of 3.3 with a load current, maximum load current of 0.5 amps. Since this is not always the case and the load continues to be changing all the time, you only need a mechanism where this resistance can also be altered at all times, right. In other words, this is nothing but the source, this is nothing but the drain of a MOSFET, and this change essentially is nothing but the gate voltage that you are providing. In simple terms, you need to modify the resistance between drain and the source, also called the RDS. In other words, an LDO simply manipulates what LDO? LDO's control loop simply manipulates the series elements RDS, nothing else than this. This is indeed the truth. That is all I was trying to get at. Okay. And if you note this, so in other words, NMOS N channel MOSFET typically has RDS very low, you want less than 1 ohm, maybe 0.5 ohms, maybe 0.1 ohms, and so on and so forth. The lower the better, right. You will still be able to pass a lot of current with hardly any voltage drop across the device, and yet provide a large amount of load current, and that is why its response is also really very good, and we described the dynamic response of an LDO in our previous discussions. So, compared to NMOS, PMOS or P channel MOSFET, RDS is quite high. That is all we are trying to say. I would not like to give any numbers because each manufacturer specifies different values, but you have to note that essentially we are trying to, with all this control loop technology, we are actually trying to vary the resistance between the drain and the source very effectively, and that is how the regulator is able to keep itself is able to provide the required assistance for us. Alright. Now, so this is one important thing which you have to note. We can put down very simple equations for power dissipation. Power dissipation, let us put it down. Power dissipation at the output simply is nothing but the V out times the I out current, right. You can do this, and input power is also important, but it is quite simple, it is nothing but V in times the I in current, and what is important is the power dissipation of the LDO. This is very important. This is nothing but V in minus V out times I out, output current, nothing but the drain current as we called it. But please note, some amount of current is also consumed quietly, quiescent current, for the LDO to function. So, we may want to add the quiescent current as well. So, since the quiescent current is very small, you can approximate the power dissipation of an LDO as V in minus V out times the load current, which is I out. Okay. So, that is a very important thing. Here if you just to complete the discussion here, you can see that we had to provide sometimes, in order to ensure that the regulator of an N channel MOSFET is under providing a regulation, we had to provide sometimes higher voltage at the gate, and this is typically done using a charge pump. Charge pumps are another kind of devices which essentially are built inside the LDO, but you can also buy them outside. Essentially use is nothing but a voltage multiplier, okay, and so it is nothing but a voltage multiplier, and we will see how to build these for the purposes of our work at a subsequent time. Alright. So, this is one part of the story. The other part of the story is indeed that you may have to look at a data sheet and understand several parameters of an LDO. So, let us put down some important parameters for this LDO and also see if we can actually conduct an experiment, understand the experiment well, and then come back and put the theory, our understanding behind that experiment, and then summarize everything about the LDO. I would like to stop here.